Good morning. Thank you to everybody for attending this new session of Doctoral Meeting, presented by Laura Vicente, entitled Energy Efficient CMOS Power Management Units for Energy Harvesting Applications. Well, a few words about Laura. She studied physics, like me, at here in this university, and she got a master's degree in microelectronics in Sevilla, in the University of Sevilla. She is pursuing a PhD here with Paula and Oscar Pereira. Okay, you have more or less 20-25 minutes to explain the main contributions of your work, and after that there are a lot of people here to ask questions, okay?
Yeah, perfect. Thank you so much for the introduction, and thank you everyone for being here. And well, I'm gonna talk you a little bit about my work, which is about energy efficient power management units for energy harvesting applications. This is the outline of the topics we are going to address. First of all, I will start with a brief introduction about general energy harvesting. And then my PhD has been divided into two approaches. That is, harvesting energy from DC sources, mainly being photovoltaic, and harvesting energy from AC sources, mainly piezoelectric. So we are going to address those topics. And lastly, I'm going to finish talking a little bit about the future work. So first of all, what is energy harvesting? Energy harvesting is the process of converting ambient energy into usable DC electrical power. There are several sources of energy available in everyday life, such as light, temperature gradients, mechanical vibrations, or even RF. Each of these sources needs its transduction mechanism in order to convert that energy into the electrical domain. However, the electrical energy these transducers produce cannot be directly employed to supply electronic applications. Why? Because the output they have is usually with very low voltage, and since we are dealing with ambient energy, the conditions of operation are quite unpredictable. Therefore, we need what are called power management units. The work of the power management units is to boost, to regulate, and to optimize that energy harvested. Amongst the main applications that benefit from energy harvesting solutions, we can highlight IoT networks, wearable devices, and even implantable. So in the first part of this presentation, we are going to address photovoltaic energy harvesting. The power generated by a photodiode can be expressed as this curve. This is the power that a photodiode generates. You can see that there is a point where this power is maximum. In order to maximize this generated power, power management units include what is called a maximum power point tracking algorithm. So they force the operating conditions of the circuit in order for it to work at this point. However, this traditional approach neglects the impact of the interface circuits. And what we state is that the maximization should be performed here, directly on the load. And we are going to prove it mathematically. So to do so, we develop a model of a harvester, and we consider that the PMU is mainly composed of a DC-DC converter. So using typical equations of DC-DC converters and considering its typical loss of mechanisms of losses, we get that the current entering the charge pump can be expressed as this. So I will use charge pump and DC-DC converters as synonyms, so please don't get confused. From typical equations of the photodiode, you get that the current that it produces is this. So we can solve this. You can solve this for the input voltage, and you will get this. I know this is a funky looking expression, but it's going to be extremely useful because it is going to allow us to quantify both the input power and the output power analytically. And we did so. This is a representation of the input power and the output power, both as function of the frequency and of the load resistance. And you can see that, in fact, the input power behavior does not match the output power behavior, and therefore maximizing the input is not equivalent to maximize the output. In fact, we can calculate the frequency that maximizes the input for each load resistor and the frequency that maximizes the output for each load resistance, and we will get this. In orange, we can see the frequency that maximizes the input, and that is the available power, and in blue, the frequency that maximizes the output. And in fact, they are not the same. If we were to calculate the difference in the power, we can see that maximizing the output yields up to a 20% more power. Therefore, our approach is more beneficial in terms of power provided to the load. Now that we have demonstrated it analytically, we wanted to design a circuit that implemented this approach. So we designed it in 180 nanometer CMOS, and we implemented an algorithm that tracks the output and maximizes it by tuning the frequency of operation. So I'm gonna provide a breakdown of each of the blocks. First of all, we have a charge pump. The charge pump is a cross-couple voltage doubler, but with a twist. The novelty here is that the gates of the transistors are driven by using boosted signals. These boosted signals are generated using both of these structures, and what we achieve with this is that the transistors have a better driving capability because you are increasing its gate-to-source voltage. And we compare this new topology with the traditional cross-couple, and what we observe is that the topology we propose compared with the classical one, the one we propose increased the range of operating conditions. Next, the oscillators. Oscillators are an electronic block that provides the clock signals that drive the circuits. And we use a relaxation oscillator topology, a typical one. And in this structure, the frequency of the clock signal is proportional to this capacitor. So what we included was a capacitor bank that is several capacitors in parallel that can be connected or disconnected by a switch that is controlled by a digital word. So what we achieve with this is that we can tune the oscillator in order to provide different frequencies of operation. This digital word is provided by a control unit. The control unit has been designed in Verilog and then synthesized. And what it does is that it performs what is called a perturb and observe algorithm. If you're not familiar, perturb and observe algorithm, what it does is the following. So it reads the output value and it stores it. Then it performs a perturbation. The perturbation is performed, as I said, by changing the capacitor active in the oscillator. Then it reads the new value of the output and it compares both. If the new value is higher than the previous one, then the perturbation is kept. On the other side, if it's not, the perturbation direction is reversed. Then we have implemented a sample and hold comparator. Nothing fancy here, it's just to store the values of the output and to compare them. And we also wanted to implement a startup so that the circuit is able to start from a cold state without needing any external boosting signal. So to do so, we included some level detectors. We performed some transient simulations. Here you can see the output voltage as a function of time, and we also included the bit that is currently active on the capacitor bank and the equivalent frequency of operation in the oscillator. And here we can see that the circuit is able to start from a cold state and enters normal operation in just a few microseconds, pretty quick. So it enters normal operation, the algorithm starts working until it finds the optimal operating point, and then it oscillates around it. So this is the operation. We wanted also to check the efficiency of the system. To do so, we perform a lot of Monte Carlo simulations. That's where the error bar comes from, accounting for the standard deviation of these simulations. And you can see that we are able to achieve almost an efficiency of 80%, which is pretty nice, actually. We also included a power breakdown of the losses, and we can see that the charge pump is the most power-hungry block as expected. So this has been, well, not exactly this, an improved version of this system has been fabricated. We just received it some months ago, and I'm currently testing it. So this is the fabricated, this is a chip, this is a photo of the chip. And to test it, we also have to design a PCB. This is just a screenshot from the design tool. And these are some pictures I took yesterday of the PCB with the different components soldered, and there we have the chip. You can see it's just this tiny thing here. And as you can see from the wire mesh, this is currently under testing right now. So that would be all regarding the photovoltaic, and now we are going to move to our AC source, that being piezoelectric. For those of you who are not familiar with piezoelectricity, piezoelectricity is a phenomena that some crystals present where when you apply a mechanical stress on them, they react by producing an electrical potential. This is a very cool phenomena, and some state-of-the-art solutions are actually exploited to perform energy harvesting applications. However, we have observed that there is a lack of theoretical background justifying design choices. So we wanted to just study a little bit the charge extraction process and to derive some analytical expressions. This is a typical piezoelectric transducer model. It's composed of a sinusoidal current source, there you can see, and also a capacitor, the piezoelectric capacitor. The voltage that accumulates in this capacitor has this form. You can see that first the voltage on the capacitor increases until it reaches a maximum, and then since the current becomes negative, it depletes the capacitor, and so on and so forth. So how can we harvest the energy from the piezoelectric? Well, one common method, it's called synchronous electric charge extraction. So this method does the following. First, it lets the transducer work in open circuit mode. That is, it just stores charge on the capacitor. However, when the capacitor reaches a maximum on the voltage, then we connect some kind of harvester circuit that depletes the charge in the capacitor as quickly and efficiently as possible. Then we open the circuit again, and you can see the idea, right? However, this is the ideal behavior. This is not what we are going to have in real life. In real life, real circuits are going to behave something along the lines like this. So, open circuit is the same, but real-life implementations of harvester are not able to completely deplete the capacitor in such a small period of time. And what happens is that there is always some remaining charge in the capacitor. We are going to call this remaining voltage residual voltage, okay? we are going to call this residual voltage, and we wanted to analyze the impact of this residual voltage in the overall performance. So to do so, we did something along the lines of what we did in the photovoltaic case. We proposed a model, we derived some equations, we solved it. I'm going to save you the boring parts, and this is the result. So we found that you can express this residual voltage as an alternating series of this form. And this formula, what it does, is that it allows us to quantify the impact of this residual voltage as function of the operating conditions of the harvester circuit and its impact on the energy. So we plotted, and here we have the normalized. In order for you to hear me, I need to be close to the microphone. So here we have the normalized energy extracted and the residual voltage, and we have plotted them as a function of the operating conditions of the harvester. So we can clearly see that the best extraction profile happens here, where the residual voltage is almost zero, and we get all of the energy possible. However, this would be at the cost of having a harvester working with very demanding operating conditions, which will make it a very, very power-hungry block, having a lot of losses. So we can see that there exists a clearly trade-off between the energy that can be extracted and the power losses of the harvester. But hopefully, with the equations we just provided, you can quantify this trade-off and find a sweet spot. So yeah, that would be all, and I wanted to talk a little bit about our future plans. So regarding DC harvesting, we want to extend the results of the photovoltaic harvester to thermoelectric energy harvesting. Thermoelectric energy harvesting is also a DC source, but it's quite tricky because the transducers have a very, very low voltage. So it imposes some very tricky operating conditions that we need to overcome. We have some ideas, and our final objective would be to fabricate a chip that is able to accommodate both of the sources. And regarding the piezoelectric harvesting, we just want to implement an experimental prototype. So that would be all. Thank you so much for the attention.
Thank you. A very interesting talk.
Thank you so much.
A little bit different that
Yeah,
we are used to
quite different, yes.
hear. But well, anybody has some questions?
So thank you for the presentation. I wanted to ask more in the DC energy harvesting management unit. Can you display the layout of the circuit?
The layout, well, I don't have the picture here. You will need to guess it from here, which is not. You wanted to see this picture. Okay,
So,
yeah, tell me.
Can you detail more about the area overhead of the power management unit here?
Yeah, this is actually, it's not so high. If I recall correctly, this is just, the power management unit is duplicated 4 times here. We wanted to, this is a typical practice. We don't implement just one. We implement the circuit several times in order to test different things. So here you can see 4 different power management units with different test structures. And actually each one of them, this is, I think it is 700 microns. And height and width is just 300 microns. It's quite of a small. I think the area was 0.3 square millimeters. So yeah, we were happy with the area consumption. What you see here is just capacitors. This is just, we have 6 capacitors. The char pump has 6 capacitors. Each of them is a capacitor. And I don't know if, well, some of you, I know you are from electronics, so you might be familiar, but to design, when you are designing the layout, you have several metal layers. So, for example, for designing these capacitors, we use the 5th metal layer and the 6th metal layer. So behind that, behind that you still have a lot of metal layers. So here you see the capacitors, but beneath here we still have a lot of circuits. So I'm sorry that I don't have a picture of the layout, because here you cannot see, but I promised you, here they are a lot of circuits, trust me. So here we have the charge band, the oscillator, all of that. Then this is just some digital parts, and this is the buffers driving the output. And then it goes to the paths, the typical stuff. This is just some custom paths we wanted to test, and we are currently just testing it. So yeah, this would be all. I'm sorry, I'm just showing you the capacitors and asking you to trust me. But maybe then I can show you the layout and show you the different layers if you're interested.
Thank you.
No, thank you.
Another question? Well, I have
Tell me.
questions that is more or less curiosity by my part. One of them is what is the percentage of the energy that these circuits consume respect to the amount of energy that it can be managed?
Yeah, okay. So I assume that you are asking regarding something around this line. So you can see that here, this is just the peak efficiency. We put the power breakdown of this peak efficiency case, and by having an 80%, that means that from the 100% of energy you are able to use from the photodiode, you get to the load an 80%. However, we are not, this is a bit tricky, we are not actually considering a real photodiode. To perform this testing, we didn't consider a real photodiode because we were not able to integrate it. So we are considering 100% of efficiency from what you are actually able to harvest there. What we should do is provide, and it's future work we wanted to do it, is provide what is called the end-to-end efficiency, that I assume this is where your question was going. That would be, if we are working here, then assume, okay, this is the energy you are losing, and consider also the power losses, right? That was something around. But we actually calculate the point of operations, and we get that we were losing almost close to, the ideal point of operation is not here, but it was something around here. So if I recall correctly, the energy loss between the maximum available was just at 10%. So maybe that would be the 80% of the 10%, so of the 90%. They were quite efficient. We were really happy with that. In fact, I told you that this is an improved version because we were not happy with just having this point here. We wanted to, because you can see that the peak efficiency is really high, but it's narrow, this peak. So we wanted to extend this to a wide range of operating conditions. And we did it, but unfortunately, I don't have the experimental results to show you. So hopefully, in the future, I will show you some better results than this.
Will you present your PhD?
I hope so. Yes. Yes.
Another question is a general question. Yeah. In the second part, in the piezoelectric work, you need to do a force or something like that to the crystal.
Yes. Yes.
But the energy for doing that.
Where does that came from? Yeah,
well,
we are thinking on real life applications. So this would be, for example, using what is already present in everyday life. For example, the vibration of a train. You go on a train and the railways go like tu. So imagine if you just put a piezoelectric device there, and you're producing the energy. So it's an energy that is already on our everyday life, but
Okay,
just
okay.
use it. Yeah.
'Cause
Actually, if you
I
let
missed
me,
this one.
if you let me, I saw that there are pretty cool applications where they introduce piezoelectric in pacemakers. So the heart itself produces the movement, and as a result of the movement of the heart, you power the pacemaker. That's amazing,
Yes.
for me at least. Yeah.
Yes, yes. Okay, another question? Okay, we can, thanks again.